short. Other than some introductory material that you need to read through, I'm just going to kind of give you an introduction to statistics and why we're interested in statistics, but also just some terminology and some different things that you have to kind of be aware of when we're learning statistics. So first of all, what is statistics? In the previous screencast, I did go through this in a little bit more detail. I like to think of statistics as the art of learning from data, using data to guide the decision-making process. We use sample data to make inferences about the underlying population. Many statistical tests use mathematical equations to arrive at a conclusion. So a lot of this course and the next course, part 2, you're going to be doing a lot of mathematical tests and using mathematical equations to arrive at a conclusion. In statistics, we are also interested in visual presentation of data and our results. So we're going to kind of mix that in throughout our analyses. So in this screencast, I'm just going to go over the basics. I'm going to cover the types of studies that statisticians use. I'm going to talk about deterministic versus stochastic processes. And then I'm going to talk about correlation versus causation and confounding factors. And these are all important things that you need to consider when we're studying statistics. So let's talk about the types of studies. The first type of study that we'll talk about is known as a retrospective study. This just looks back at historical process data to examine the relationship between two variables. Importantly, for retrospective studies, no direct experimentation is necessary. We basically use old data that's already been collected. So if you were looking for, trying to correlate different toxins that might have been found in water to incidence of cancer, you could just go back historically, the last couple decades and look at water test results and cancer results in different areas and sort of put together relationships that way. Observational studies are very similar to retrospective study in that you're just looking at information, looking at data, but it observes the process or population during a period of routine operation, but usually the process is not disturbed. A designed experiment, in contrast, is where controlled or deliberate changes are made in the controlled variables, also known as factors, to study the relationship between those variables and the system output. This would be something that's very inexpensive, very easy to manipulate. You can do a lot of runs, experimental runs at different combinations of all your variables or factors. At the end of the specialization, part 3, I'm going to kind of show you how you can go about designing experiments. But typically, if something is really expensive, it takes 2 weeks to make a batch of pharmaceutical drug, for example, you're not really going to be able to do designed experiments because you need a handful up to dozens of experiments to really go about a designed experiment. However, designed experiments are used in optimization. And again, I'll talk about that in course 3 of the specialization. The next thing we're going to talk about is deterministic versus stochastic processes. A deterministic process is one whose outcome is always the same, or nearly always the same. The outcome can oftentimes be modeled by an exact mathematical equation, and the outcome is very close to 100% predictable. In contrast, a stochastic process is one whose outcome involves probability and chance. Many processes, by the way, in the real world involve both deterministic and stochastic aspects. So sometimes you'll put together a model that uses deterministic mathematical equations, but then some stochastic random error is built into those parameters. Statistics allows us to analyze stochastic processes. So really what we're going to be talking about in this entire course in the 3 parts relates to stochastic processes. Let's take a look at a couple examples of deterministic processes. Again, the outcome is always the same or nearly always the same. For example, the time it takes for a washing machine to run a load of laundry. It's just kind of an automatic machine and it's kind of just doing its thing. It's got very carefully timed cycles. So that's an example of something that's always the same. The time it takes for a penny to drop from 10 feet in a controlled environment room. The pressure of a container given the amount of gas and the temperature. Again, I'm a chemical engineer. So PV equals nRT, some of you might be familiar with that. Physical things in the universe are highly governed by deterministic mathematical models. Driving an empty highway under ideal conditions at a constant speed of 60 miles per hour. So that's another thing that would be better modeled as a deterministic process. So now let's look at a couple examples of stochastic processes. These involve probability and chance. So the number of green M&Ms in a bag of M&Ms, that's going to be variable. So that's going to involve probability and chance. The numbers on dice. So you roll a pair of dice on the table. Those numbers are probabilistic and they totally depend upon chance. The weight of a burrito made at the local burrito stand. There's going to be some average burrito weight, but you're going to have some sort of standard deviation or variance. The drive time across a city. So you have stoplights, traffic, other disruptions. And if you did the same drive across a city at the same time of day, you'd have kind of a distribution of the times it takes to get across the city due to these things that you cannot control. Weather patterns obviously are very stochastic. There's all sorts of uncertainty, probability, and chance involved with those. Stock market fluctuations, highly variable, lots of probability and chance involved. And if you took buyers who basically on paper they look exactly the same, have the same demographics, age, salary, sales preferences are going to be completely variable. And so that's another thing that's a stochastic process. So now let's talk about correlation, causation, and confounding factors. Correlation refers to how variables move relative to one another, and this will become more clear in a moment. Two variables are positively correlated if a change in variable x is associated with a change in variable y in the same direction. If I look at a scatter plot here, we have y on the y-axis, x on the x-axis, and you see that positive deviations in x result in positive deviations in y. Negative deviations in x in general result in negative deviations in y. And so this is known as positive correlation. Two variables are negatively correlated if a change in variable x is associated with a change in variable y in the opposite direction. So here, a positive change in x leads to a negative change in y. Likewise, a negative change in x results in a positive change in y. So these variables are negatively correlated. So these are important terms to know in statistics. And two variables are uncorrelated if a change in variable x is not associated with any change. So a change in variable y in either direction. Here, we see that if you increase x or decrease x, you really don't see a positive or negative correlation. So these are uncorrelated. There is no correlation here. Causation relates to the cause and effect nature of a variable. If a variable influences another variable, then there is a causal relationship between those variables. For example, the cause, you flip on a light switch. The effect, the light turns on. Or another example, a man smokes a pack of cigarettes every day for 30 years. The effect, he gets lung cancer. So these are examples of cause and effect. Causation oftentimes gets confused with correlation. Just because two variables are correlated does not mean that one causes the other. So let's look at an example here, and this is going to bring about something known as a confounding factor. A study finds a strong correlation between level of physical activity and incidence of heart disease. And what they find is those who exercise more have a lower incidence of heart disease. So level of physical activity strongly affects the incidence of heart disease. And what they find is as level of physical activity increases, the incidence of heart disease goes down. If you take a look at the study, the people that are involved in this plot shows the participants in this study and the age and the exercise per week. You definitely see those who are older exercise a lot less, and younger participants exercise a lot more. So really, if you're looking at this, you might consider that age is affecting things here. In other words, level of physical activity is highly dependent upon age, as I showed in that previous plot. Older people have a lower level of physical activity. It's also well known that older people have a higher incidence of heart disease. And so looking at this, there definitely is a correlation between level of physical activity and incidence of heart disease, but there's a confounding factor, and that confounding factor is age. Age is having a direct effect on both of the things that were being correlated, level of physical activity and incidence of heart disease. When there's a factor that does this, this is known as a confounding factor, and it really weakens the study quite a bit. It's a lot better to take this into account before designing the study. A much better study would have been to look at activity levels of a much narrower age distribution. So if age was not a confounding factor, then this study would have been a lot stronger. So what I'm showing here is correlation does not imply causation. The underlying cause for incidence of heart disease could just be age because of the way that this study was designed. Some other examples that are just kind of comical. We have per capita cheese consumption correlates very well with the number of people who died by becoming tangled in their bed sheets. So there's a strong correlation there. Or the divorce rate in Maine correlates quite strongly with the per capita consumption of margarine. You got to be really careful. Even though things are correlated, does not imply that there's a cause and effect relationship. So hopefully this screencast gives you kind of an introduction to some of the important things that we need to consider when we learn statistics.